Hello, everyone. Thank you for joining this webinar today. I'm pleased to be with Dr. Ben Sumanov and Dr. Miao Zhang to show you the opportunities that we see from building and pavement LCA to inform concrete industry value chain scope 1, 2, 3, and avoided emissions. So to start this presentation, I just wanted to bring you a very brief introduction that why this problem matters and what CS Hub has done so far. Then I'm going to hand it over to Bensu to continue the presentations. We will continue with Miao, and then we will have Q&A at the end as well. So to start, we see that there is a great momentum around doing life cycle assessments and environmental product declarations to answer the question of the global warming impact performance of different types of cement-based products, for example, ready-mix concrete or precast products. And we see that each company has usually published a handful of EPDs, for example, to disclose the environmental impacts associated with each product. But typically we see that each company is producing 10 to hundreds of different types of products over their physical annual year, for example, and each of them has been produced hundreds of times, not to mention thousands, depending on the plant size. So there is a lot of operations going on. So we not only have the diversity of the product, but also different volumes of the products produced in a given year. And EPDs and LCA only shows us a snapshot of a small proportion of the GHG performance of these mixtures. The other important factor is that when we look at the EPDs, we are very well aware of the amount of GHG emissions associated with the upfront emissions, but we see that these products, these cement-based products, are fashioned into different types of end-use applications. On the right bottom, you can see that we have, for example, cement and concrete used for buildings, residential or multifamily, commercial. We also have for infrastructure applications, pavements, etc., that each of these have their own use phase and end-of-life emissions. And it can vary significantly from 1 year of operation to another year, depending on the market proportions and the size of the company. So we need a more comprehensive framework to draw around the organizational footprint of a given facility that produces these materials. To that effort, we see there are multiple guidelines and solutions for CO2 accounting and reporting. For example, this report that I show you on the screen, published in 2005, that is addressing the smokestack and electricity consumptions emissions associated with a given plant, for example, a cement plant here. But again, there is no clear guidelines on the rest of the emissions, the downstream emissions associated with the use and end of life, as well as the other upstream emissions associated with the procurements of the raw or intermediate materials for that cement plants. Here, Bensu and Miao will provide guidelines on how to comprehensively assess the manufacturer footprint from an organizational perspective and accounting for all these important parts of the product use as well. The other part that I wanted to emphasize is that when we look at a facility and they are looking forward to improving the performance of their product, so producing a high performance product that will give a lower use phase impact. And again, I'm emphasizing on expanding the facility. So with the expansion of their market and producing more of these materials, they will make their footprint goes up. But in reality, with using these products, which is more efficient, then we would have a lower use phase or end use impact. So if we want to show that, we will see that it doesn't show up in the scope 1, 2, 3 emissions. So there's a negative point here for the factory. For example, the example that I brought up here is the tire industry, and the tire industry has already come up with the guidelines how to quantify the excess fuel emissions associated with the tire performance during its use period. But we will see that if we only look at the limited scope of the GHG reporting currently existed in the literature, we only have the raw material procurement and manufacturing emissions. And perhaps distribution was added if downstream processes was included, but the use and the benefits that they would give to the user as a result of expanding the high performance product was generally neglected. Here, we will show you how we can estimate the environmental benefits that an organization, for example, a cement or concrete facility, can bring by producing a more efficient product in different end-use applications. So I'm going to stop here. I'm going to hand it over to Bensu for the rest of the presentation to share her insight about how we can develop such guidelines for building sector, and followed by Mia, who will show us how we can use it for pavement sector. Bensu, the stage is yours.
Awesome. Thank you for the introduction, Hassam. And I would like to thank everybody who's attending today. And just because we got a clarifying question about what an EPD is, Hassam, either you could step in or I could explain, but an EPD is usually a document that includes production, transportation, and installation emissions associated with a product like cement or concrete. It's often defined as including all life cycle emissions, but it's usually limited to the A123 emissions. So as Hassam mentioned, my name is Bensu, and my colleague Miao Zhang, we're going to talk about opportunities for building and pavement life cycle assessment to inform cement scope 1, 2, 3 and avoided emissions reporting. And if you guys need any further explanation about anything that's on the slides, feel free to add that into the Q&A, and I'll make sure to address them during my presentation. So this webinar will include two parts. In part one, I will first give an overview of cement's value chain, and then I will present a map of building life cycle emissions and the portion of these emissions which we've identified as reportable within cement greenhouse gas accounting and reporting. And then I will show a case study of scope 1, 2, 3 emissions in a US context. And in part two, my colleague Miao will give an overview of stakeholders throughout the cement's value chain. Then she will present a map of pavement life cycle emissions and the reportable emissions we've identified in that realm. And then she'll present a case study of scope 1, 2, 3 and avoided emissions. And I want to take a moment to talk about what we do at the Concrete Sustainability Hub. Our research is broadly collected under three main themes: carbon neutrality, infrastructure, and resilience. And details about our research and research briefs and papers can all be found on our website, csub.mit.edu. And the work that we're going to talk about today actually combines research from all three of these themes. With the part that I'll be presenting on building life cycle assessment, this includes work that could be found under our resilience and carbon neutrality themes. And the way that resilience ties into this is because it involves characterizing the building stock to estimate expected damages. And then we've used that building stock modeling in scaling up our life cycle assessment and carbon reporting. And then the section on pavement life cycle assessment, in turn, could be found under our infrastructure and carbon neutrality themes, which Miao will cover in part two. So let's dive into it. What's missing in the literature relating to carbon accounting or greenhouse gas accounting? So present protocols that are available for GHG reporting or greenhouse gas reporting currently lack clear guidelines for material sectors and specifically producers of intermediate products. And I will be talking about GHG protocols, but first let's talk about the cement's value chain. The cement's value chain has three scopes: scope 1, 2, and 3. And scope 3 in turn is divided into upstream and downstream portions. Scope 1 comprises of direct emissions, so emissions related with cement production, since we're talking about cement's value chain. And what determines the amount of emissions in this scope is the energy intensity of cement production. Scope 2 includes emissions associated with the generation of purchased electricity. So those are fuels burned for the production of electricity, which are used in Scope 1. And this depends on the local composition of energy resources. So an area with lower carbon energy resources or renewable energy resources will have lower Scope 2 emissions. Scope 3 includes all the other emissions within the cement value chain, which includes the upstream emissions associated with the extraction and production of materials, raw materials such as limestone, as well as downstream emissions associated with activities like transporting cement or cement-based products to the construction site, the construction of the building and the installation of these cement-based products into the building or the end-use application, as well as the use and end of life of the final products, which are buildings and pavements. And these emissions include, in pavements, that would include the fuel consumption of cars, and in buildings, that includes the energy consumption of occupants in these buildings. And the GHG protocols includes definitions for Scope 1, Scope 2, and all the categories that I just mentioned for upstream and downstream Scope 3, as well as more categories on top of that. But then guidance that's produced specifically for cement, such as WBCSD guidance, only requires a select few of these emission categories to be reported on. And those specifically are emissions related with the production of purchased goods and services, the production of capital goods, fuel and energy related activities, and downstream transportation and distribution of cement-based products. And then all the other categories are deemed optional on the basis of cement being an intermediate product or these categories being irrelevant. And the relevance relates specifically to items like leased assets or franchises. The ones that are eliminated on the basis of cement being an intermediate product include emission categories like the use and end of life of sold products. And that's relating to, so these guidance claims that it's too difficult and too complex to measure or even model these emission categories. Despite the fact that when we look into the details of the examples of emissions which could be reported on, when we look at the use and end of life of sold products, these relate, so like for instance, the use of sold products, it's deemed optional and it includes the indirect use phase emissions of sold products over their expected lifetime, including the indirect consumption of energy, such as fuels and electricity. And as an example, they give emissions arising from the use of buildings and roads. So this guidance itself acknowledges that the end product of cement producers is buildings and roads, not just cement. So the present protocols for cement specifically lack clear guidelines, particularly for the Scope 3, despite the fact that there's actually growing emphasis on the benefits in this scope. For instance, if we look at PCA's roadmap to carbon neutrality, this includes several items of how we could reduce emissions by addressing Scope 1, 2, as well as some of the categories that are currently required to be reported on, but then several of them relate to benefits that would be reaped during the use or end of life of buildings or pavements. And then as Hassam mentioned, with the two examples of double versus single glazed glass, as well as fuel efficient versus regular tires, we're seeing industries actually reporting on Scope 3 emissions. because when producing these more efficient products, we may see an increased scope 1, 2, or upstream scope 3 emissions. But then we see net benefits in a reduced downstream scope 3 emissions, as overall these products lead to reduced societal emissions. Let's talk about what we found in our case study of scope 1, 2, 3 emissions. The case study that I'll be presenting today is on Miami, which is located in Southeast Florida in the United States. And specifically, I'll be talking about our modeling of single-family homes and how that could be mapped onto cement scope 1, 2, 3. The building stock could be represented as a combination of different building archetypes. And the building archetypes for single-family homes include concrete masonry, and wood archetypes. Let's talk about building life cycle results that we could get from analyzing a single year of added building stock as a combination of these three options. Oftentimes when we look at studies of building emissions, most of these studies include emissions associated with producing materials, transporting them to the construction site, and installing them during the building construction. These are emissions that fall under the embodied category. And in our study, we've expanded the embodied emissions to include not just the initial construction phase, but also the production, transportation, and installation emissions associated with repair and replacement, where replacement relates to regular wear and tear, and repair relates to major repairs after, for instance, natural hazard damages, as well as the end of life of all of these products. Our study also includes an operational component, which is comprised of the energy usage for buildings. So here, I would like to tie into our first interactive question, which, Andrew, could you please pull that up? So the question is, which of these building-related emissions that we see on the slide are relevant to a cement producer's environmental footprint? I want you guys to select all that apply, regardless of whether it's a portion or the entirety of the listed activity. So regardless of whether we're reporting on, for instance, all of building energy usage or only a select portion of that. I'll give you guys a couple minutes to think about and answer that. Yeah.
No, that was interesting. Thanks very much, Bensu. Especially this pie chart, when I look at this and I see the materials production contribution to total life cycle GHG emissions is as large as the repair GHG emissions, and almost 3/4 of the total emission goes to the energy usage. I just want to hear your thoughts and insight about how do you think that these proportions vary when we change the context from one location to another or one country to another?
Oh yeah, definitely. So going from one location to another, this could change the composition of materials that are used in our buildings. So for instance, lower carbon materials and lower carbon building design will lead to a lower portion of this dark red section. In areas that are less exposed to wear and tear damages, the replacement could be lower, less exposed to hazard damages, or a different type of hazard damages could lead to higher or lower repair portion. And using materials that have a higher thermal resistivity in the building envelope could lead to a lower portion of energy usage. So it's a combination of the building design, the type of materials that are used, as well as the climate and natural hazard exposure that are going to affect the proportions of this distribution.
Awesome, thanks very much. So when the context varies, so we have to take a look at both the design and materials from a building life cycle perspective, as well as thinking about what kind of consequences we would expect in terms of the natural hazards, the dominant parameters, for example, from a hazard perspective. as well as the climate conditions, like how much cooling and heating demand we would need. Awesome. I appreciate that.
Thank you.
Can we see the results if everyone got a chance to vote?
Okay, so if you wouldn't mind, I'm going to go ahead and read off the answers. So if you put everything but producing lighting and appliances used in the building and electricity consumption for lighting and appliances, you are correct.
Thanks for sharing that, Andrew. So moving on to how these life cycle emissions relate to the environmental footprint of cement producers. As the question implied, we do believe that a portion of each of these life cycle stages is relevant to cement scope 1, 2, 3. So that includes the production, transportation, installation of cement-based products, either used in the initial construction or repair and replacement activities, as well as the end of life of these products. And we attribute a portion of the building energy consumption, which we've called the excess energy, and I will define that in a second, also to cement scope 1, 2, 3. And if you take these slices and put them together into its own pie chart, then we can see that emissions related with the building use comprise a large portion of what we're identifying as reportable building emissions, which can be computed with building life cycle assessment. Let's talk about excess energy. In the definition of excess energy, we wanted to hit all principles of greenhouse gas reporting. So we wanted to make sure that we accounted for building energy for completeness, that we apportioned it for cement-based products to keep things consistent because that's what we're reporting on. We wanted to identify the portion that's relevant. So not all of the energy usage we think is relevant to report. Specifically, the heating and cooling could be impacted by the cement-based products used in the building facade or exterior wall core, but the energy consumption associated with, for instance, lighting and appliances will not be affected by cement-based products, so that falls outside. And we're proposing a science-based metric to achieve this attribution or apportionment. Two methods that we've considered. First, we considered doing it by mass. And although this is common for other emission categories, it's not meaningful for this one because the density or the mass of products that are used in the building exterior wall core don't necessarily correlate with the thermal resistivity of these materials. So we decided to apportion heating and cooling emissions by a performance metric. So thermal resistivity has a relationship for systems in parallel. So for instance, windows, doors, and the exterior wall system all contribute to the thermal resistivity of the structure, and they're found in parallel, as in the same plane with each other. And then the exterior wall finishing, core, and interior are systems that are in series. So we needed to consider both systems to attribute heating and cooling emissions to the exterior wall core where cement-based products could be found. This is also the amount that would be reported for a building with a wood exterior wall core would be 0 because there wouldn't be cement-based products in the wall core. So building life cycle emissions include the product, construction, use, and end-of-life emissions, which we just talked about in the pie chart. It also includes negative emissions, such as carbon uptake, which occur during the building use and end-of-life phases. And as I just mentioned, all of these, or at least a portion of each of these building life cycle stages are relevant to report in the environmental footprint of cement producers. For instance, the production of cement for initial construction, repair, and replacement maps onto scope 1, 2. The production of raw materials used for the production of cement map onto upstream scope 3. And anything that happens after the production of cement, such as processing cement into cement-based products, transporting, installing, and the end of life of these cement-based products, as well as excess energy and carbon uptake map onto downstream scope 3. So going back to our case study of single-family homes in Florida. With information about market share, we can model how reportable emissions evolved over time. And our study started from 1940, which is the first date that we have a complete set of information for, through 2022. As you can see, with scope 1, 2, and upstream scope 3 emissions, these more or less follow the pattern of cement consumption over the years, where it's going up over time and then taking a dip around the 2008 economic crisis. But then with downstream scope 3, again, it's following a similar trend, as in like it goes up and then it goes back down, because we also have these installation and construction emissions in downstream scope 3, but we also see it's kind of like a cone and it's growing over time because we have more buildings contributing to the energy consumption emissions and more buildings reaching their end of life and contributing to end of life emissions. If we take only buildings built in 1940 and look at this relation cumulatively, then we can look at how the different emission categories add up together over our analysis period. So towards the end of the analysis period, scope 1, 2 comprise 26% of what we've identified as reportable emissions. And this includes the calcination and combustion of raw materials, the combustion of fuels on site, as well as the combustion of fuels for purchased electricity, which map onto scope 1 and 2. And in the current guidance for cement reporting, all of these categories are deemed required. Upstream scope 3 comprises 3% of reportable emissions towards the end of the analysis period. And this includes cradle to gate production of raw materials, capital goods, and fuels that are burned either in scope 1 or 2, as well as the transportation of these raw materials, capital goods, and fuels to the location where they're consumed. And again, most of these categories are required under the WBCSD guidance. And then downstream scope 3 comprises 71% of reportable emissions towards the end of the analysis period. And this includes processing cement into cement-based products, transporting these products, installing them during building construction, as well as the excess energy use of buildings with masonry or concrete cores, the end of life of cement-based products. And here you can see that a large portion of this comes from excess energy, and a similar yet smaller portion comes from the end of life of buildings. As well as on the negative side, there's also carbon uptake during the building use and carbon uptake at building end of life. So scope 3 not only comprises a large portion of what we're identifying as reportable emissions, it also spans a large variety of different emission categories. But then only one of these emission categories is required under the WBCSD guidance, and that's the transport of cement-based products. And that's actually the tiny sliver of emissions that are in this scope. So not only can life cycle analysis results be manipulated to map neatly onto the greenhouse gas protocol's emission scopes and categories and capture a wider range of emissions than is currently required, it creates opportunity to expand this suggested or required reporting to better track industry goals, which relate to a lot of these downstream impacts, such as the use and end of life of buildings and pavements. Our main contributions in this field, apart from mapping life cycle assessment onto greenhouse gas reporting, has been calculating the repair and replacement emissions of buildings so that we're accounting for embodied impacts in the use phase, not just initial construction, defining excess energy as there hasn't been a precedent for this in the building or construction materials sectors, and calculating carbon uptake during use and end of life. As well as accounting for impacts induced by the surrounding neighborhood, which could affect the amount of repair and replacement, excess energy, or carbon uptake. So that kind of affects all of these other categories. And we have ongoing research on each of these contributions. They're actually separate papers or fields of research that we have going on. And we have analogs in the pavement sphere as well, which my colleague Meow Meow is going to talk about now. That's my email address if you guys want to reach me. It's my name, bensu@mit.edu. And with that, I'll pass it off to Meow Meow.
Yeah. Hi, everyone. My name is Meow Meow Zhang. Andrew, could you please open my video setup? So I cannot share my video now. Yeah. Yeah, great. Yeah. Hi, everyone. My name is Meow Meow Zhang. Today, I'm going to discuss the second part of today's presentation. And for today's presentation, I will discuss 3 contents: the scope 1, 2, 3 in pavement value chain, avoid emission, and scope 1, 2, 3 with footprint reduction and avoid emissions, the comparison of these 3 aspects. So at first, let's make a simple comparison between the scope 1, 2, 3 and product LCA. The scope 1, 2, 3 focus on the organizational footprint, while LCA is individual product or service specific. The scope 1, 2, 3 accounting is sector-based and it is reported annually. But for the product LCA, it evaluates the entire lifespan of the product or service, and it is phase-based evaluation from the cradle to grave. Therefore, the scope 1, 2, 3 is used to track and report annual organizational JJ footprint, while product LCA is for environmental impact assessment and alternative comparison. Many companies are required to report their scope 1, 2, 3 based on the JJ protocol. For example, tech companies such as Google and Apple, they are also required to report their scope 1, 2, 3. Here is an example of the scope 1, 2, 3 of the Apple company. They reported all their scope 1 and 2 and 3 emissions, and we can find that the scope 3 emissions accounted for the majority of their emissions. Let's back to the pavement. So pavement life cycle JJ emissions includes multiple aspects from material acquisition, material production, construction, operational use phase, the maintenance and the rehabilitation phase, MR, and end of life. The use phase emissions include emissions from multiple aspects. At first and most importantly, the PVI emissions, pavement vehicle interaction emissions. It accounts for the emissions from vehicle fuel consumptions. The pavement performance, the pavement condition can affect the PVI emissions. So compared to a smooth pavement surface, a rough pavement surface will require the vehicle to use more fuel to overcome the rolling resistance. It leads to a higher PVI emissions compared to the smooth pavement surface. And fuel cycle emissions, which is cradle to gate emissions of fuel consumed by vehicles. We also reported fuel cycle emissions as operational emissions because they are directly proportional to the amount of fuel used and the PVI emissions. Albedo effect, the pavement surface color is also important. A light pavement surface, light colored pavement surface with higher albedo will reflect more solar radiation, and this effect is equivalent to the albedo emissions. And carbon uptake, some pavement materials, such as concrete, will absorb CO2 from the atmosphere through a process called carbonation. So the concrete pavements will have negative carbon uptake emissions. And for lighting emissions, these are emissions from the street light and the signal lights. And traffic delay emissions, they are additional emissions caused by traffic delay due to MR activities. So the use phase emissions are very important. So in pavement life cycle JJ emissions accounting, we may find the use phase emissions are even higher than the embodied emissions. And use phase emissions are different for different pavement materials. So in this figure, the concrete pavements and asphalt pavements, they have different use phase emissions. So it's very important to account for use phase emissions in pavement life cycle JJ accounting. So Benzu just discussed the definition of scope 1, 2, 3 for one specific company, the cement company, and I'll go deeper into the scope 1, 2, 3 definition for the entire pavement value chain. The pavement value chain involves stakeholders from primary material company, mixture company, construction company, DOT, fuel providers, end users, and waste services. Each of them will generate their own emissions as their scope 1 and 2, and all stakeholders in the value chain are responsible for all emissions. For example, for primary material company, they generate emissions related to the material acquisition, and this part of emissions are their scope 1, 2, and the remaining are their scope 3 emissions. And mixture companies are directly responsible for emissions from material production, and construction companies are directly responsible for emissions from construction phase. And the remaining as their scope 1 and 2, and the remaining emissions as their scope 3. And the same idea can be applied to all stakeholders. And this is a full mapping of scope 1, 2, 3 to different stakeholders. The maintenance and rehabilitation, the MR part, is a simple duplicate of the new construction part, because MR also includes process from material acquisition to construction to the use phase. Yeah. And all stakeholders in the value chain are responsible for all emissions, and they are mapped to scope 1, 2, 3 according to the stakeholders' roles and activities. So here, Andrew will help us to set up a pool activity here. So this pool is about a question of payment value chain scope 1, 2, 3. So considering U rule in the payment value chain, which of the following is the largest source of U emissions? So please consider U rule in the payment value chain and select the option best reflects your stakeholder perspective. Yeah.
Awesome. Thanks very much, Miao. It's a very interesting figure showing that everyone is responsible for the life cycle emissions. Some of them have directly have influence on the changes that we can make in order to reduce the scope 1 to 3 emissions, and in some part there is an indirect signal that we may need to communicate with our downstream users or upstream suppliers in order to reduce it. I would be curious to hear your thoughts on the proportions of the scope 1 to 3 from a Department of Transportation, the DOT perspective. What could they do? Like, what are these parameters that are under their direct control that they could do in order to reduce their emissions?
Okay, so for DOT, the emissions are under their direct control is scope 1, 2 emissions. But as I mentioned, each stakeholder is responsible for all emissions. So DOT can do everything, make every effort to reduce the payment life cycle JJ emissions and their scope 1, 2, and 3 emissions. So for example, in terms of scope 1 and 2, which is related to the pavement albedo and carbonation emissions, they may choose light colored concrete pavement surface to reduce the scope 1 and 2 emissions. And for upstream scope 3 emissions, which is related to the embodied emissions of pavement infrastructure, and they may select lower embodied emissions pavement materials to reduce their upstream scope 3. Regarding to the downstream scope 3 emissions, which is related to the PVI emissions, they may want to maintain the pavement performance to a better level. by doing more MR activities to reduce the PVI emissions and their downstream scope 3 emissions. So every efforts they can make to reduce the payment life cycle GHG emissions and their scope 1, 2, 3. Yeah, that's it.
I appreciate that. Thank you. Now I'm looking at the poll results. There's a diversity of responses here. 40% downstream scope 3, 20% upstream scope 3, 32% scope 1, which is the direct emissions, and 8% scope 2 indirect emission. So why don't you enlighten us with the next part of your presentation to show how significant it can be?
Okay, yeah. I'll explain the scope 1, 2, 3 calculation for a concrete pavement by case study here. And this slide shows a case study design for an interstate in Arizona. So this figure shows the scope 1, 2, 3 for concrete pavement for different stakeholders from cement company, concrete company, construction company, DOT, and end users. The figure at the right hand shows different components of the concrete pavement GHG emissions, and they are mapped to different, mapped to scope 1, 2, 3 for different stakeholders. In this figure, the scope 1, 2 are colored in orange, and for cement company, the emissions from material supply and transportations are their scope 1 and 2. The albedo and carbonation emissions are negative for concrete pavements, so they are emissions below the zero line. So the scope 1 and 2 emissions are colored in orange. We can see the scope 1 and 2 emissions moving across different stakeholders. And different stakeholders will have very different emission profiles based on their respective roles and activities. Among all different stakeholders, the cement company holds the greatest scope 1 and 2 emissions. So it shows significant potential for footprint reduction in the raw material supply phase of concrete pavements. So for a company who improve its products to have a lower GHG emission products, the company's scope 1, 2, 3 will decrease, and the emission reduction can be evaluated by footprint reduction, this concept. And it is reported that the use of slag can reduce the concrete GHG emissions. So for concrete company, if the concrete company uses slag in their concrete production, their scope 1, 2, 3 will decrease because of the use of slag. And for our case study in Arizona, currently there are about 20 miles of concrete pavements, and the concrete scope 1, 2, 3 will decrease by could decrease by 30 kiloton because the use of slag, and the concrete footprint reduction is about 30 kiloton. Here is an example from a published report. They calculate the environmental benefit from the use of recycled materials and the use of mixed fuels. It's very similar to our case study of footprint reduction, but they define it as avoid emissions. So what is avoid emissions, and is there any difference between avoid emissions and footprint reduction? I just discussed the concept of scope 1, 2, 3. The scope 1, 2, 3 framework is used to know, report, and reduce footprint. The scope 1, 2, 3 is very important, but incomplete. I will introduce another concept, the avoid emission, as a complementary to the scope 1, 2, 3 framework. And the avoid emissions, which can go beyond footprint reduction, which emphasize proactive efforts for positive environmental change. Okay, the avoid emissions refer to the positive impact on society when comparing the environmental impact of a solution to a reference scenario. So the avoid emission is the emission difference between two scenarios, the solution and the reference scenario. The solution emissions refer to emissions that occur with the solution being implemented, and the reference emissions refer to emissions that would have occurred without the solution. So for our case study, if we assume concrete pavements as a solution and asphalt pavements as a reference, the positive impact of replacing asphalt pavements to concrete pavements can be evaluated by the concept of avoid emissions. And here is a case study of the avoid emissions from switching asphalt pavements to concrete pavements. And this figure shows the life cycle emission comparison between these two pavement systems. And concrete pavement, because concrete pavements have negative emissions caused by the carbonation and albedo, so the actual concrete pavement life cycle emissions start at these star points. Yeah. And the life cycle emissions difference between these two pavement systems are the avoid emissions. And the figure at the right hand shows the detailed comparison between these two pavement systems. For embodied emissions, concrete have higher embodied emissions than asphalt pavements. But when we consider the use phase, concrete actually has lower use phase emissions compared to asphalt pavements. So that's why concrete pavements have like lower total life cycle emissions compared to asphalt pavements. And here is a comparison between the avoid emission concept and the scope 1, 2, 3 emission, and why we need this avoid emissions concept to complement scope 1, 2, 3. So for company A, who implements the low emission solution, if we expand the sale of the low emission products, the scope 1, 2, 3 of company A will increase because of the expanded market share. Correspondingly, for company B, who is displaced by the solution, their scope 1, 2, 3 will decrease because of the contracted market share. If we combine company A and company B, we may find that the planetary emission reduced and the total emission reduction can be evaluated by the concept of avoid emission. So the expanded sales of low emission products will increase its scope 1, 2, 3, but it will automatically lead to lower planetary emissions because competitors' emission decrease. And this emission reduction cannot be captured by scope 1, 2, 3 because the scope 1, 2, 3 of company A increased. And the avoid emission is the only way to show how solutions lower the planetary emissions. And for our case study in Arizona, currently there are 2% of concrete pavement. If we expand the concrete market share from 2% to 10%, the concrete scope 1, 2, 3 emissions will increase by about more than 200 kilotons. Correspondingly, for asphalt pavement, their market share will be contracted from 98% to 90%, and asphalt scope 1, 2, 3 will decrease by about 700 kiloton. So if we combine the emissions of concrete and asphalt company, we may find the total emission reduction is about 432 kiloton, and this is the avoid emission of switching of expanding concrete pavement from 2% to 10%. And the increase in the use of concrete pavements will increase its scope 1, 2, 3, but decrease the planetary emissions. So overall, in this presentation, I introduced the two ways to reduce JJ emissions, the planetary JJ emissions. The first one is to reduce the concrete JJ emissions by the use of slag in the concrete production. And the second one is to expand the concrete market share from 2% to 10%. By combining these two methods, the concrete scope 1, 2, 3 increase, and the asphalt scope 1, 2, 3 decrease. And the planetary emission reduction is about 462 kiloton. For this 462 kiloton emission reduction, the two concepts of footprint reduction and avoid emissions are both involved. And how to differentiate these two concepts, the footprint reduction and avoid emission. So first, currently in Arizona, there are 2% of concrete pavements. For these 2% existing concrete pavements, the concrete scope 1, 2, 3 reduction caused by the use of slag is classified as footprint reduction. And on the other hand, for the new 8% concrete pavements from switching asphalt pavements to concrete pavements, and the emission reduction is classified as the avoid emissions. footprint reduction focus on emissions reduction within the product value chain. So we use internal footprint reduction here. And avoid emissions involve emission reductions occurring outside of the value chain, and it is always related to the market change. So the footprint reduction can be captured by scope 1, 2, 3 concept, while avoid emissions cannot be captured by scope 1, 2, 3. So that's why we need this new concept, the avoid emission concept, to show the benefit from alternative products and market change. Both internal footprint reduction and avoid emissions are key concepts for climate change mitigation. By implementing both approaches, organizations can effectively contribute to planetary emission reduction. So in conclusion, the avoid emissions is the only way to show how solutions lower the planetary emissions, and both internal footprint reduction and avoid emissions are key concepts for climate change mitigation. Yeah, that's it. That's my part of presentation. Thanks all for listening. Yeah.
Awesome. Thanks very much for this great presentation. I think now we can see how we can, harness the power of LCA and calculate the amount of organizational footprints associated with two main end-use applications of cement-based products. Thanks very much, everyone, for posing your question in the chat box. I'm afraid that we may not be able to respond to all of them, but I'm trying to bundle some of these questions that are relevant together and ask it from our presenters. First question, how did you calculate the CO2 uptake during the use and end of life? Could you comment on that, please?
I guess either of us can answer this question, but we have extensive work on modeling the surface area and volume of cement-based products used in buildings and pavements. We have a conference paper out there, and soon our journal paper will be out there too, but on the CSM website, and I could share that in the chat, we have a calculator tool which helps estimate the CO2 uptake over the use and end of life, defining things like the lifespan, the end of life period, the stockpiling geometry, as well as the cement composition and other factors like the compressive strength. Oh, thank you, Andrew.
Awesome, thank you. Miamia, a specific question from your presentation. Is the data in the figure that you showed that, visualize the contribution of scope 1 to 3 emissions to each pavement stakeholder? Yeah. Is it as an example, or can it be generalized to any pavement segments?
Any pavement segments. Okay, so for the case study, the scope 1, 2, 3 for concrete pavement specifically, it's a case study for interstates in Arizona, and it has its specific traffic volume, the pavement materials, and MR activities. So I would say the scope 1, 2, 3 for different stakeholders would be different for different pavement segments. But the main conclusion that the use-based emissions is higher than the embodied emissions, or the a cement company holds the largest share of scope 1 and 2 emissions, should be a more common conclusion for all concrete pavements. Yeah.
Perfect. Thank you. Question about carbon capture and sequestration. Is it part of scope 1 or 2 or 3?
For the pavement value chain. Okay, so for the pavement value chain, the carbon uptake emissions is a use-based emission because it happens in the use of the pavements. Mm-hmm. And the use, this part of emissions could be scope 1 and 2 of DOT, because the carbonation emissions are directly generated by the pavement itself, and the pavement are properties of DOT. So the carbon uptake emissions are scope 1 and 2 of DOT, but they are scope 3 for other stakeholders. It could be upstream scope 3 emissions for end users, and downstream scope 3 for the material company and construction companies. Yeah.
How about the carbon capture at the cement plant? Is it part of the scope 1, 2, or 3 of the cement manufacturer? Both of you can jump in, please.
So the carbon Carbon capture and utilization or storage would be a method of neutralizing scope 1 emissions if it's applied at the cement plant, but it could also be applied by different stakeholders. So it could also affect scope 2 emissions or scope 3 emissions too, possibly.
So depending on the method, it can be applied and attributed to each of this scope. Plus, we have to use a lot of electricity, so that could be part of scope 2 of the cement plant as well.
Fair.
Yeah.
Awesome. Then, so about the excess energy consumptions in buildings, could you elaborate a little bit how it differs from the total energy consumptions and how you did this, maybe briefly?
Oh, okay. So that the excess energy is still a philosophical discussion that I would appreciate input on, but the way that we thought about it is the baseline. It is possible to have buildings with no heating and cooling requirements, such as the passive house standards. So taking that as the ideal case, any any heating and cooling that's not zero is going to be accounted for by some stakeholder. And then the way that we decided on what portion could be attributed to cement-based products is accounting for the thermal conductivity of windows, which are going to be affecting the heating and cooling demands, that of doors, which is a way smaller surface area, but they're still there. And then looking at the thermal resistivity, or like when divided by the thermal conductivity of the exterior walls and how that compares to windows. So that's going to be different for a wood archetype, a concrete masonry or concrete block archetype versus a like cast in place concrete archetype. All of these typically have different R values for the material itself, as well as the building wall systems are designed with different levels of insulation. So taking account all of those factors and doing that attribution.
So only a fraction of the total
Only a
energy
fraction.
consumption was attributed to the cement-based products or the walls in general. All right, thanks very much. We are already 1 minute after the hour. We make sure to address your question and get back to you through emails. Again, I apologize for not being able to go through all the responses and questions. I'm going to hand it over to Andrew to adjourn for today. Thank you.
All right, fantastic. Thank you all for your presentation, and thank you for your participation and attendance to everyone in the audience. So as Hassam mentioned, we couldn't get to all of the questions, but fear not, at MIT, no stone goes unturned. So we'll get back to you with answers on that. I just wanted to alert you to some other things coming your way relevant to this webinar. So we're going to distribute the recording, the slides, and I also wanted to let you know that we have 2 research briefs coming out on these topics, one of which covers novel frameworks to assess the value chain for materials producer, and the other is a framework to assess value chain emissions for the pavement sector. So look out for those, and thank you very much. If you have any questions, these 3 have very straightforward emails. It's just their first name at mit.edu. So for example, Hassam at mit.edu. So with that, have a great day, and I hope to see you soon.